So for today's agenda, I will first go through the Flink setup at Robinhood. Next, I will go through the Apache flink-kubernetes-operator that we use to manage our Flink applications. Third, I will go through a health check mechanism that we implemented in our in-house deployment system to monitor the status of our Flink applications and to handle rollbacks. Fourth, I will talk about the checkpoint fetcher software that we developed to reduce manual operational toil on deployments. In the end, I will conclude with future work we have on a roadmap for Flink. At Robinhood, all of our Flink applications run on Kubernetes. We have multiple Kubernetes clusters in our production environment, and the majority of our Flink applications run on one Kubernetes cluster. To manage all of these Flink applications in their lifecycle, we use the open source Apache flink-kubernetes-operator, and we have tuned certain configurations in the operator in order to handle our deployment patterns, which I will go through more in detail in the next slide. We currently have around 250 Flink applications, and most of the use cases are for ingesting data from my Kafka topics and storing them in S3 for compliance. We also have applications that are used for fraud detection, which monitor anomalies and trade orders to our market makers, and applications that are used for shareholders' positions, which determine in real time whether a Robinhood user is eligible for a shareholder event. For the fraud detection, shareholders' positions, and other use cases, Flink is used to ingest data from Kafka and store them in different data stores. Out of the 250 Flink applications that we have at Robinhood, we have to deploy 125 of them concurrently for our data ingestion use case. When we first tried to deploy this many Flink applications concurrently, the operator pods would crash, and this would cause some of the Flink applications to get deleted and recreated. The application pods were getting deleted and recreated because of a leader election issue in the operator pods. In particular, when the standby operator pod was becoming the leader, the old leader pod wasn't killed, and both old and new leader pods would actually conflict each other, resulting in the deletion and recreation of a Flink application. To fix this leader election issue, we decreased the number of operator pods to 1 so that multiple operator pods weren't stepping on each other in managing a Flink application. The operator version we were using at that time was 1.6, and as far as I'm aware, this leader election issue is fixed in a future version after a bug fix was merged in the underlying Java operator SDK. After the number of operator pods was decreased to 1, although the Flink applications don't get deleted anymore, the operator pod would still crash when we deployed a large number of applications concurrently. We went through the operator documentation and found a lot of parameters that we could tune. So we tuned different parameters on the operator in non-production environments, ran load tests by creating a large number of Flink applications concurrently. On the slide, I have listed 3 of the parameters that we have tuned so that the operator wouldn't crash during large deployments. All of this tuning essentially slowed down the deployment process of the Flink applications and ensured that the operator pod didn't crash. If you're interested in understanding what these parameters are, you can check out the Flink operator documentation or come talk to me after this presentation. At Robinhood, we have our own in-house deployment system for deploying applications. In this deployment system, a version refers to the commit in our GitHub repository. We want to continuously deploy the latest version so that the latest code is deployed, even though most of the time there are no changes in the Flink application itself between these versions/commits. Whenever a Flink application is deployed, our deployment system monitors the following field in the Kubernetes custom resource Flink deployment: lifecycle state. By the way, this Kubernetes custom resource is exactly the same as the one you get when you use the open source Apache flink-kubernetes-operator. When the Flink application is deployed, The job status and lifecycle state fields progress through different values as the application is coming up. And over here on the slide, you can see an example of the job status and lifecycle state field of a Flink deployment custom resource. When the application is healthy, the job status field becomes running and the lifecycle state becomes stable. In our deployment system, we implemented a health check to monitor the lifecycle state field of a Flink application during deployments. Based on this field, if the Flink application doesn't become healthy within a certain period of time, then our deployment system will roll back the deployment by deleting the new version and deploying the previous version of the application. We have had scenarios where the Flink applications crashed, and the only way to recover them was to manually delete them and redeploy them. Once a Flink application is deleted, the operator doesn't know what the latest checkpoint or save point is for this application anymore. So you would need to find the path of the latest checkpoint or save point in AWS S3 for our case. Populate this field in your YAML manifest for your Flink application, and then deploy the application. To reduce any human errors that could occur while recovering a Flink application from the latest checkpoint, we created a software called the checkpoint fetcher to automate a lot of this manual work. The checkpoint fetcher software scans both checkpoint and savepoint folders in AWS S3 for the latest path and sends this path to our in-house deployment system. The deployment populates the field initialSavepointPath with this path in the Flink deployment custom resource before deploying the application. Essentially, if an application team needs to deploy a Flink application after it has been deleted, they only have to click on the deploy button in our in-house deployment system. And the system will handle all of this manual work and start the application from the latest checkpoint. At the end of the day, the checkpoint fetcher reduces operational toil in Robinhood when application teams need to recover their Flink applications. Up until now, I was talking about the work that our team has done so that application teams can continuously deploy the latest version of code for their Flink applications. Some items on our roadmap to enhance our Flink setup include active-passive setup of a Flink application across multiple Kubernetes clusters. Currently, we have multiple Kubernetes clusters, and if an application team wants to deploy their Flink application on all Kubernetes clusters, then they need to set up the application in active mode across all Kubernetes clusters. This means that the downstream sinks/consumers need to be able to handle duplicate state or data. Ideally, application teams would like to set up their Flink application in active-passive mode so that if one Kubernetes cluster fails, the Flink application fails over to another Kubernetes cluster. This will require developing a controller that monitors a Flink application across multiple Kubernetes clusters. Last of all, we would like to enable Flink autoscaler for cost reasons. Most of our data ingestion jobs have high traffic during market hours or certain hours of the day. And ideally, we want to scale our Flink applications appropriately so that we are not overusing resources during low traffic hours. This will lower the overall cost of our Flink applications. That's all I have for today's talk on Robinhood's Flink deployment practices. And I hope this provides insights on how you can enhance your Flink deployment setup. Thank you all.